Oh, yeah. Okay. We're going to do two operations on vector fields today, and neither of them are particularly difficult. One of the operations is going to give you a vector field, and another operation is going to give you a scalar field. But both of these operations occur on vector fields, if that makes any sense. So you've got the vector field P, I, Q, J, and R, K. First operation is called the curl of F, and there's a formula for it. But the best way to remember how to calculate the curl of the vector field is to do it as the determinant with the IJK across the top. Right here you put just partial of something with respect to x. Right here you put the partial of something with respect to y. Right here you put the partial of something with respect to z. Then you put P, Q, and R down there, and you calculate that determinant. And I'll show you that in a minute. And you're going to get a vector field. Okay, and this vector field is associated with rotations. If you think of fluid, it gives you, the curl gives you the amount of rotation around an axis that points in the direction of that vector, of this vector right here. Okay, so if you've got water spinning, all right, the direction is the curl, and the length of that vector gives you how fast it's spinning around that point. Like whirlpools, exactly what I think about. Yeah, and like the length of that, and then the distance of the length of that gives you how fast it's spinning and all that. But so it's like fluid flows and electrical flows and all that kind of stuff like that. Okay. So, and we're going to use this as a way to tell whether a vector field is conservative. If you have a three-dimensional vector field, all right, you know if it's two-dimensional, to tell if it was conservative, you just compare your partials. Like if you had a vector field that was just P, I, and QJ, then if you were going to tell if this was conservative, you'd take the partial of P with respect to Y and see if it's equal to the partial of Q with respect to X. If it was, then it's conservative. Or for a three-dimensional vector field, we didn't have a method until this. If you want to tell if a three-dimensional vector field is conservative, then you see if the curl is equal to 0. So if the curl of F is equal to the 0 vector, then F is conservative. Okay. All right, so let me look at a problem with this before we go on. Say number
It's not spinning, right?
is not spinning. You're right. Just kind of like a lazy, just kind of pond or something.
Body of water.
Yeah, with no spin to it. If I look at number 2, f of x, y, z is x to the third y z squared j plus y to the fourth z to the third k. And I'm asked to find the curl of this thing. Then I'm going to set this up, ijk, the partial with respect to x, the partial with respect to y, the partial with respect to z. Then I don't have an I, so that's 0. My j, x to the third y z squared. And then for this one, I have y to the fourth z to the third. All right, does everybody understand what I'm doing? That's just the partial of whatever with respect to x, partial of whatever with respect to y, partial of whatever with respect to z. Okay, I do cofactor expansion. I've forgotten how y'all do this, but that's what I do. All right, so I have I multiplied times. All right, when you multiply these two, this means take the partial of this with respect to y. Does that make sense? Do I need to write it down? The partial of this with respect to y is going to be 4y to the third z to the third minus, when you come back, you're taking the partial of this with respect to z, which is x to the third, oops, how about 2x to the third? 2x to the third yz minus j. So cross this out. So now I need the partial of this with respect to x, which is 0, minus 0 times the partial, that's 0, plus k. Partial of this one with respect to x is 3x squared yz squared minus the partial of 0, which is 0. So let me see if this is going to simplify at all. That's going to be 0. This is going to give me 4y to the third z to the third minus 2x to the third yz. That's my I hat. That's 0 plus k hat, which is 3x squared yz squared. This is a vector field. This is the curl of your function f. And it is a vector field. Take the curl of a vector field and you get a vector field. Okay? All right. The other operation we're doing besides curl is called the divergence of f. Of your vector field, and it's the same thing. Pi plus q j hat plus r k hat. And the divergence of f is going to give you a scalar field. So the divergence of a vector field is a scalar field. And it is going to be this, the divergence of f. Symbol is div. It is the partial of p with respect to x plus the partial of q with respect to y plus the partial of r with respect to z. And that's it. And the divergence is the net change of the mass of the fluid that's flowing with respect to time. So this is a change of the fluid as it's flowing with respect to time. Now I can go back to the same problem up here and find the divergence of this same problem. So the divergence of this function, sorry, that's not right, I have to put a vector. The divergence of the vector field, the partial of p with respect to x is 0 because there is no p term, it's 0, plus the partial of, this is my q, with respect to y, that's x to the third z squared, plus the partial of this one with respect to z, which would be 3 y to the fourth z squared. So the divergence is just the sum of these. X to the third z squared plus 3 y to the fourth z squared. Okay. Do I need to do another curl or another divergence? They're pretty straightforward. Okay, to determine if a vector field is conservative, let's look at number 14. They're going to give you a vector field. And this one is x, y, z to the fourth. x squared z to the fourth j plus 4x squared yz to the third k. They want to know if this is conservative. All right, this is three-dimensional. So to see if it's conservative, you need to set up your curl and see if it's equal to 0. So ijk. Partial with respect to x, partial with respect to y, partial with respect to z. So x, y, z to the fourth, x squared z to the fourth, and 4x squared y z to the third. All right, so I, partial with respect to y, is 4x squared z to the third minus the partial with respect to z, which is 4x squared z to the third, minus j. Partial with respect to x is going to be 8x yz to the third, minus the partial with respect to z, rats, which is going to be 4x yz to the third, plus k. Partial with respect to x, 2x z to the fourth minus the partial with respect to y, x z to the fourth. And it's not going to be 0, so it's not going to be conservative, but I'll go ahead and finish it out. This one is going to be 0. So minus j, 8 minus 4, 4xyz to the third, plus k hat, x z to the fourth. It is unequal to 0, therefore this is not conservative. I was actually hoping it was going to be conservative, because if it is conservative, I have to go back and find the original function. Did I lose anybody, or did I make a mistake?
I figured it out.
Okay. You do want your credit, don't you?
Right. You should.
All right, if it is conservative, they want you to go back and find the potential function, which is actually what you did in the last section. Do I need to look for one that is conservative to go back and do that? Because this one is not, but maybe 13 is. Yes, go ahead and find it. Is it? It is. It. Does everybody feel the same way? I don't have to? And you're saying, sure, go ahead. Okay. All right, do you want me to go through the steps showing it's conservative?
No, you don't have to do that. I got it.
Okay, but you said it's conservative. You looked in the back of the book, and number 13 is conservative. Huh? Has an answer. Okay. All right, so it's conservative. Everybody they went through the step, and you got zeros. Okay? Everything's zeroed out. So it is conservative. So to find the potential function in number 13, here's your vector function, or your vector field. Y squared z to the third, 2xyz to the third, j, 3xy squared z squared. Okay. It is conservative. We're going to say the curl, oops, not the CO, the curl, the CU. The curl of f is 0. Therefore, all right, we know by definition this first term p is the partial of some function with respect to x. That's y squared z to the third. So integrate this with respect to x, and that's going to give you f is x y squared z to the third plus some function that is in terms of y and z possibly. Now we take the partial of this function f with respect to y. The partial of the first term with respect to y is 2xyz to the third plus the partial of g with respect to y. Compare this to the second term in this vector field. Compare it to 2xyz to the third. These two are exactly the same, which means the partial with respect to y is 0, which means that this function must not have had a y in it at all, but it might have had a z in it. So that implies that g of yz is only a function of z. So f must look like xy squared z to the third plus a function of z. So now take the partial of this with respect to z. Partial of f with respect to z is 3xy squared z squared plus g prime of z. Compare that to the third term, which is 3xy squared z squared. And lo and behold, those match exactly, which means g prime of z is 0, which implies that it must be a constant. So your function is c equal to xy squared z to the third. Oops. So you're going back to the conservative stuff that you did before. Okay? Now the only other problems that you have to do is one like number 12, where it's actually deciding if these statements mean anything the way they're written, or whether they do not mean anything the way they're written. Now, going back, first of all, when you take the curl of a vector field, you get a vector field, okay? When you take the divergence of a vector field, you get a scalar field. The other thing they have in here is a gradient vector. Now we took the gradient vector of a function. We didn't take the gradient vector of a vector field. We do, and we get what? A vector field. Exactly. So using this, I think I've got everything in there. You have to decide right here. You have to decide if this expression is meaningful or not meaningful. If it is meaningful, tell whether you get a scalar field or a vector field when you calculate it. Does that make sense? Mm-hmm. All right. So A, the curl of a function. Can you do the curl of a function? Okay. Can I take the curl of a function? Yes. You can take the curl of a vector field. Let me go through the other here. Can you take the gradient of a function? That's a scalar function. Can you take the gradient of a scalar function? Yes. Yes, that's meaningful. What do you get? You get a vector field when you take the gradient. Okay. Divergence of a vector field gives you a scalar field. Okay. Can you take the curl of a gradient vector? All right, what do you get? Vector field. Is everybody following? All right, can you take the gradient of a vector field? No. Can you take the gradient of the divergence of a vector field? Yes, you can do that. Okay. The divergence is a scalar field, and you take the gradient of the scalar. And what do you get? You get a vector field. All right, can you take the divergence of the gradient of a function. What do you get? Scalar. Can you take the gradient of the divergence of f?
Is that divergence of that? Doesn't have to be a vector field.
The first one gives you a scalar. And the gradient will give, you can take the gradient of the scalar.
You can take the gradient of scalar.
So my question is,
Oh, I'm
the
sorry.
way it's written is
You do that one first.
divergent of a function is not of a vector field, right?
Yes, you're right. You can't even do that one. You can't do that one. You have to start on the inside, so yeah. Very good. Can you take the curl of f? Can you take the curl of f? Let's start in the center.
Yeah.
Yeah, well, can you take the curl of that? Okay, what do you get? Vector. Can you take the divergence of the divergence of that? No. Okay, cross product. This is cross product. You've got the gradient of f and the divergence of f. Can you take the cross product of those two things? No. Yeah, one's a scatter, one's a vector. Okay, this one. Can you take the divergence of the curl of the gradient? Start on the inside. Can you do the gradient of f? Can you take the curl of whatever you get there? Can you take the divergence of the whatever that is? Okay. Okay. Okay, so that is all there is to this section 16.5.